Hello everyone, this is lecture 10, vector value functions. So since pre-calculus to calculus 1 and even in physics, you learn about certain type of force. Most of the time we use vectors to represent static quantities such as constant force applied on some object or constant velocity on a boat in a current. Starting from this section, we're going to put vectors in motion by introducing vector value functions or simply vector functions. So our task is to investigate the graphs of vector value function and to study them in the setting of calculus. So that means that everything you already know about limits, derivatives, and integrals can be applied to this new family of functions. So to get to the details of vector value functions, we start imagining a projectile moving along a path in three-dimensional space. It could be an electron or a comet or a soccer ball or a rocket. If you take a snapshot of this object, its position can be described by a static position vector r equal to x, y, and z. However, if you want to describe a full trajectory of this object as it unfolds in time, you must represent the object positions with something called a vector value function, such as you have the vector r of t is equal to x of t, y of t, and z of t, whose component change in time. That's the idea of vector value functions that we're going to look at. So hopefully at the end of this lecture, we could be able to write the general equation of a vector value function in component form and of course in the unit vector form. We could be able to recognize parametric equations for a space curve. Let me first give you the definitions of vector value functions. So functions of the form r of t equal to x of t, y of t, z of t may be viewed in two different ways. First way, it is a set of three parametric equations that describe a curve in space. Those equations are x of t, y of t, and z of t. So again, it is a set of three parametric equations that describe a curve in space. In addition, it is also a vector value function. So that is using the same setup here, that is r of t equal to x of t, y of t, and z of t. We can view this particular equation or function as a vector value functions, where x of t, y of t, and z of t are the components of R. So where x of t, y of t, and z of t are components of R of t. So that is, each component varies with respect to the parameter t. So the component x, y, and t are the functions of t. That means each component varies with respect to, so WRT means with respect to the parameter t. So it depends, of course, it depends on the situation. We may have different values of t, or we have a different domain of t. There's a lot of practical applications related to vector value functions, so often the parameter t can be represented as time. So the graph of a vector value functions of the form r of t equal to f of t I plus g of t j. It consists of the set of all the points t, r of t, and the path it traces is called a plane curve. And we're going to look at an example a little bit later, but this is the definitions of two-dimensional plane curve, where f of t and g of t are the components of the vector value functions. The vector value function is written in terms of the standard unit vector form. And similarly, if you define a vector value function in three-dimensional space, it is written as r of t equal to f of ti plus g of tj plus h of tk. And this is a three-dimensional space curve, right? This consists of the set of all the points t, r of t, and the path it traces out is called a space curve. And again, this vector value function is written in terms of a standard unit vector form, and f of t, g of t, and h of t are the components of r of t. So how to graph a vector value function? As the parameter t varies over a certain interval, each value of t produces a position vector that corresponds to a point on the curve, starting at the initial vector r of a and ending at the terminal vector r of b. So in this case, you have the vector r of a is called the initial vector, because in this case, for the space curve of r of t equal to f of t, g of t, and h of t, t is between a and b. So r of a, in this case, in this particular context, is defined as the initial vector, and the ending vector is called the terminal vector. So r of b is called the terminal vector. And the vectors you see on the graph are the position vector, and it's just a snapshot of the curve in time. So here for r of t1 this is the position vector at time. This is the position vector at time t equal to t1. R of t2 is the position vector at t equal to t2, and r of t3 is the position vector at t equal to t3. Now for each t, you could be able to draw out a vector and the corresponding point, and if you connect this point together, you're gonna get the vector value functions or the space curve if you look at the three-dimensional vector value functions, or a plane curve if you look at the two-dimensional vector value functions. So again, one point on the curve corresponds to a single vector or a single position vector. So one point on the curve corresponds to a single position vector, and you can define them again as r of t. So now you have the curve here, and usually the curve is denoted as c. So that's how you plot a plane curve or a space curve. By varies the value of t, and for each value of t, you're going to have the corresponding point on the curve, and for each point on the curve, it's corresponding to a single position vector in space. So let's consider the following example. So in this example, you have a graph of an ellipse in terms of a vector value function. This is written in terms of the standard unit vector form. So r of t equal to 4 times cosine of ti plus 3 times sine of tj, and t is between 0 and 2 pi. So the starting point is t equal to 0, and the ending point is t equal to 2 pi. So here you can see on the left hand side of the screen is the table of values where I choose some point of t or some value of t's, and I want to plot the corresponding point of the curve. So this is two-dimensional case, so what you see here is a plane curve. Okay, so that's what you have to do when you want to plot a vector value function in a plane or in space. So it's not difficult to do, it's just very time consuming to do so, especially if you have more complicated vector value functions. For instance, if you look at the following curves, so for this curve, this is the graph of a circle, but the circle gets shifted up by 1 unit in the z directions. So this is the circle shifted up by 1 unit. So you have the vector value functions of the form cosine of t, comma sine of t. So the first two components represent a circle. For the z component equal to 1, that means you push this circle up by 1 unit. Similarly, if you want to plot this vector value function, you're going to set up the table, you're going to vary the value of t, and then you find the corresponding value of r. And then you connect the points together and you get the plot of a vector value functions. Similarly, for the case of the helix, you have this one is the helix, and the vector value function is of the form cosine of t, sine of t, comma t. So in this case, the z part or the z component is of the function. The first two components again represent a circle. That means when you project this helix onto the xy plane, you're going to see a circle. To plot this helix or this space curve, you're going to vary the value of the t. In this case, you can choose t between negative 2 pi and 2 pi. I'm going to show you how to plot this using the website a little bit later. But you vary the value of, and you find the corresponding value of r. You connect all the points together and you have a space curve. And for the last graph, this is a toroidal spiral. And the formula is quite complicated, so I'm going to write this down in terms of the components. So x of t is equal to 4 plus sine of 20t altogether times cosine of t. Y of t is equal to 4 plus sine of 20t times sine of t. And the last component, z of t, is cosine of 20t. So as you can see, the components of the vector value function looks quite complicated. So therefore, doing this by hand could take a lot of time and effort to do so. So what I'm going to show you next is I'm going to use a website called GeoGebra.com, and it's a very powerful tool to visualize three-dimensional curves or three-dimensional surfaces. So I'm going to show you how to plot that. So in this video, I'm going to show you how to plot plane curves and space curves in GeoGebra.org. So this is a very powerful website to visualize three-dimensional object in three-dimensional surfaces. So this is totally different from Desmos.com that I showed you previously. If Desmos.com is convenient to plot two-dimensional curves or parametric curve or polar curves, using this website, you can also plot those curves, and in addition to that, you can plot vector value functions, curves, and also functions of two variables that we're going to learn later on in the course. So when I log into this website, this is the page that I'm going to see, and I'm going to choose Start Calculator here to access the graphing calculator. And from there, I'm going to show you how to plot the vector value functions curves. So this is supposed to be the screen that you're going to see. If you do not see this kind of screen, you probably want to choose this button right here. This is the drop down button where you can choose various options here when you want to just two-dimensional graphing. This is three-dimensional calculator or three-dimensional graphs, some other geometric graphing that you can use, some probability options that you can play around with, and this is the computer algebra system that you can actually do some calculations here. So I'm going to stick with the 3D calculator, and first I'm going to graph a circle which is a plane curve. The circle consists of two components. The first component is cosine of t and the second component is sine of t, and t is varied between 0 and 2 pi. So cosine of t comma sine of t. As you can see in the graph, that is the circle. And this is a three-dimensional space where the blue axis is the z-axis, the red axis is the x-axis, and the green axis is the y-axis. Let me put this in the xy plane so that you can see that it's going to be a circle. If you try to plot the vector value functions that show in the lecture notes, so the first example you have is an ellipse, right? So you have 4 times cosine of t comma 3 times sine of t. You hit enter and you're going to see an ellipse. In addition to that, there are 3 more examples that you see in the lecture notes. The first one is the circle shifted up by 1 unit in the z directions. So you have cosine of t comma sine of t. So this one is the circle in the xy plane. Now you shift it up by 1 unit in the z directions and adjust the viewpoint. You can basically drag the axis here to view the plot at a different angle. So as you can see here, so this is the circle gets shifted up by 1 unit in the z directions. Now for an helix, the formula is going to be cosine of t comma sine of t and comma t. So as you can see, this is the curve of cosine of t, sine of t, and t for t is going between 0 and 2 pi. So it's also show it in here, so t between 0 and 6.28, which is 2 pi. Now I want to adjust the value of t starting from negative 2 pi to 2 pi. So I'm going to click on that. So you can see the cursor is blinking right now at the 0. So I change that to negative times pi and I hit enter and you can see the helixes get a little bit longer. You can play around with the parameter t to see a longer helix or a shorter helix, or you can change the shape of the helix a little bit. So this one is called the circular helix because when you project this helix onto the xy plane, you can see the circle as you adjust the viewpoint here. And we also have one last example in the lecture note, which is a toroidal spiral. So the first component is 4 plus a sine of 20t all together multiply with cosine of t. That's the first component. The second component is 4 plus sine of 20t all together multiply with sine of t. And the last component is cosine of 20t. So you can adjust the axis, drag it around, and change the viewpoint to see the spiral. So as you can see, it's quite complicated if you do this by hand. So using this tool is very helpful. It's very convenient to visualize the curve in 3D space. There's a lot of curves like this that you can try out in the textbook. You can just Google vector value function in 3 dimensions or 3-dimensional curves, and there's a bunch of them coming up, and you can try it out using this particular website. So that's it for me.